In the chemistry optional syllabus, this section tests your understanding of structural models, intermolecular forces, and macroscopic properties like viscosity and surface tension. The answers below are written exactly in the style expected by UPSC examiners, structured, mathematically precise, and featuring clean derivations. Question 1. Structural models of liquids. 10 marks. Question. Discuss the structural differences between solids, liquids, and gases. Critically evaluate the vacancy theory, Eyring's model, of the liquid state. Answer. 1. Structural differences. From a molecular perspective, solids possess long-range order and fixed positions, while gases exhibit complete randomness with negligible intermolecular forces. Liquids represent an intermediate state, characterized by short-range order but long-range disorder. The packing fraction of liquids is only about 10 text, 15% less than that of their corresponding solids. 2. Eyring's vacancy theory of liquids. Proposed by Henry Eyring, this model views a liquid as a disordered solid structure containing a large number of molecular-sized holes or vacancies. The core concept: when a solid melts to form a liquid, there is a net volume increase of about 10 text 12%. Eyring assumed this extra volume is distributed throughout the liquid as discrete vacancies, or free volume, rather than uniform expansion. Dual nature of molecules. Molecules adjacent to a vacancy can jump into it, behaving like gas-like molecules with high translational freedom. Molecules completely surrounded by other molecules remain trapped in their potential wells, behaving like solid-like molecules with vibrational movement. 3. Mathematical representation. If V_S is the molar volume of the solid at the melting point, and V_L is the molar volume of the liquid, the fraction of solid-like properties is given by Fra-C V_SV_L, and the fraction of gas-like properties is. Any thermodynamic property Fx of the liquid can be written as a partition function combination of both states. 4. Limitations. While Eyring's theory successfully explains transport properties like viscosity, it is a simplified model. It overemphasizes a sharp distinction between gas-like and solid-like molecules. Modern statistical mechanics uses radial distribution functions, RDF, obtained from X-ray diffraction to give a more accurate continuous picture of liquid structures. Question 2. Temperature dependence of viscosity. 15 marks. Question. How does the viscosity of a liquid vary with temperature? Derive the Arrhenius equation for liquid viscosity and explain the physical significance of the activation energy. Delta E_text vis. Answer. 1. Temperature effect. Unlike gases, where viscosity increases with temperature due to molecular collisions, the viscosity of a liquid decreases rapidly as temperature rises. 2. Derivation of the Arrhenius-Andrade equation. According to the whole theory of liquids, for a liquid layer to flow past another, a molecule must move into an adjacent vacancy. This movement requires overcoming a potential energy barrier. The probability of a molecule acquiring enough thermal energy to jump into a vacancy follows the Boltzmann distribution law, where delta E_text vis is the activation energy for viscous flow. Because fluid flow or fluidity, phi, is directly proportional to this jumping probability, and viscosity, eta, is the reciprocal of fluidity, phi equals frac1 eta. Taking the natural logarithm on both sides, converting to base 10 logarithm. 3. Graphical verification. Plotting log_10 eta against frac1 t yields a straight line with a positive slope. Log eta, slope equals delta E_vis 2.303 r. 1/t. 4. Physical significance of delta E_text vis. Delta E_text vis represents the energy required to break intermolecular bonds and create a hole into which a molecule can move. For highly associated liquids, like water or glycerol with strong hydrogen bonding, delta E_text vis is very high, meaning their viscosity drops sharply with a temperature increase. For non-associated liquids, like benzene or hexane, delta E_text vis is much lower. Question 3. Surface tension and paracore. 15 marks. Question. Define surface tension from a thermodynamic perspective. Introduce the concept of paracore and show how it can be used to elucidate the structure of a compound with the empirical formula C_2, H_4, O_2. Answer. 1. Thermodynamic definition of surface tension. Gamma. Molecules at the surface of a liquid experience a net inward cohesive pull from the bulk molecules. To expand the surface area of a liquid, work must be done against these cohesive forces. Thermodynamically, surface tension is defined as the free energy change per unit increase in surface area at constant temperature and pressure. Units. Text JC_dot textum -2 or text C_dot textum -1. 2. Concept of paracore. Introduced by Sugden. The paracore is an empirical property that links surface tension with molar volume. It is defined by the expression where m is the molecular mass, ρ_L is the density of the liquid, and ρ_V is the density of the vapor at the same temperature. At temperatures well below the boiling point, ρ_ versus L ρ_L, so the equation simplifies to when gamma equals 1 equals V_m. Therefore, paracore is the molar volume of a liquid at a temperature where its surface tension is unity. This eliminates the effect of temperature when comparing different liquids. 3. Structural elucidation of C_2, H_4, O_2. Paracore is an additive and constitutive property. The total paracore of a molecule is the sum of its atomic paracores and structural paracores, due to bonds, rings, etc. For the empirical formula C_2, H_4, O_2, two major structural isomers are possible: acetic acid and methyl formate. Structure A, acetic acid. Structure B, methyl formate. OOCH3, COHHCO, carbon trihydride. By utilizing standard experimental values for individual components, we can calculate theoretical paracores. Atomic constants: C equals 4.8, H equals 17.1, O text in CeOH text equals 20.0, O text in ester/carbonyl equals 20.0. Structural constants: double bond CEC equals O equals 23.2. Let us calculate the theoretical value for acetic acid. Conclusion. By measuring the experimental surface tension, gamma, and density, RRHO_L, of the unknown liquid sample, we can find its experimental paracore via equals for cam, ρ_gamma caret. Whichever isomer's theoretical value matches the experimental result confirms the identity of the compound. Key tips for the liquid state chapter in